What if everything we know about human history is just the most recent chapter? Think about this. Humans appeared 300,000 years ago. We've been building cities and writing things down for maybe 6,000 years. That's 2% of our existence. The other 98%, we were here. We just weren't doing much we could see. But what about before humans? What if something else was here first? The Earth is 4.5 billion years old. Life has existed for 3.5 billion years. Dinosaurs ruled for 165 million years. And we've been an industrial civilization for about 200 years. 200 years out of 4.5 billion. Here's what gets me. If another civilization existed millions of years ago, would we even know? Would we find any trace of it? This isn't science fiction. It's a real question scientists have asked. They even gave it a name. The Silurian Hypothesis. The name comes from Doctor Who. In the show, intelligent reptiles evolved before humans and built cities underground. It's fiction. But the question isn't. In 2018, two scientists published a paper. Adam Frank, an astrophysicist. Gavin Schmidt, a climate scientist. They asked a simple question. How would we detect an ancient industrial civilization in the geological record? Not aliens, not reptile people, just the idea. If something built cities and burned fuel millions of years ago, what would be left? The answer surprised them. Maybe nothing we'd recognize. Think about what we're leaving behind right now. Cities, roads, plastic, nuclear waste. Seems like a lot. But geology works on different timescales. Give it 1 million years. The cities crumble, the roads erode. Even plastic breaks down eventually. Continental drift shuffles everything around. Subduction zones swallow entire regions. The Earth recycles itself. What's left after 100 million years? After 200 million? Almost nothing. We've found dinosaur fossils, but we've found maybe a few thousand individual T-Rex bones. Total. Ever. Out of millions that must have lived. Fossilization is incredibly rare. Now imagine trying to find the bones of an intelligent species. They'd be even rarer. Intelligence usually means smaller populations. Tool use means less chance of dying in ways that create fossils. And cities? Forget it. We have trouble finding human settlements from 10,000 years ago. Try finding a city from 10 million years ago. It would be dust. Less than dust. It would be gone. So Frank and Schmidt asked a different question. What would show up in the rocks? Chemical traces, carbon isotopes, temperature spikes, plastic residue compressed into thin layers, maybe some synthetic molecules that don't occur naturally. They looked at Earth's history. They found some interesting moments, times when carbon isotopes shifted suddenly, periods when temperatures spiked, layers with unusual chemistry. Could those be ancient civilizations? Probably not. There are natural explanations, volcanic eruptions, meteor impacts, normal climate cycles, but here's the thing. We can't rule it out completely, and that's the point. We don't actually know how to look for this. We've never tried. We've never needed to, until now. Because the same question applies to other planets. If we're searching for alien civilizations, we need to know what to look for. And if we can't even detect an ancient civilization on our own planet, how would we spot one on Mars? So what does science actually say about finding ancient civilizations? The problem with looking for ancient civilizations is that we don't know what we're looking for. We know what modern civilization looks like. Steel buildings, concrete highways, plastic in the ocean, carbon dioxide in the atmosphere. These things leave traces, but would they last? That's the real question. Not whether ancient civilizations existed, but whether we could find them if they did. Let's start with the obvious stuff. Cities. Right now there are cities everywhere. New York, Tokyo, London, millions of buildings, billions of tons of concrete and steel. It feels permanent. But permanent is a human timescale. Geology works differently. Pripyat, Ukraine was abandoned in 1986, just 37 years ago. Trees grow through the buildings now. Roots crack the concrete. Nature is taking it back fast. Give it 1,000 years. Most of those buildings will be rubble. 10,000 years, the rubble will be dirt. 100,000 years, you'd have to dig to find anything at all. And that's with modern materials. Concrete, steel, things designed to last. Ancient Rome fell 1,500 years ago. We can still see the Colosseum, but most of Roman civilization is gone, buried, scattered, recycled into later buildings. And Rome is recent, incredibly recent. What about something from 1,000,000 years ago? Nothing would survive on the surface. Wind erodes it. Rain dissolves it. Plants break it down. The Earth is constantly recycling itself. Then there's plate tectonics. The ground moves. Continents drift. Subduction zones swallow entire regions. The ocean floor gets pulled under continental plates and melted. The oldest ocean floor on Earth is about 200 million years old. Everything older has been recycled, melted down, gone. So if a civilization existed on a coastline 300 million years ago, the entire coastline might not exist anymore. It could be at the bottom of a trench, or melted into magma, or pushed up into a mountain range and eroded away. The Earth doesn't preserve things, it destroys them. What about fossils? We find dinosaur bones. Why not ancient city ruins? Here's the thing about fossils. They're incredibly rare. Paleontologists estimate that billions of T-Rexes lived over the species' existence. We've found maybe 100 partial skeletons, total, ever. That's not because we're bad at looking. It's because fossilization almost never happens. You need specific conditions. The body has to be buried quickly, usually in sediment. Water helps. Then minerals seep in and replace the organic material. Slowly. Over millions of years, most dead things just rot, or get eaten, or break down in the sun. They don't become fossils. Now think about intelligent beings. They usually have smaller populations than prey animals. They live longer. They're less likely to die in ways that lead to fossilization, and if they're advanced enough to build things, they probably bury their dead, or cremate them, or do something that prevents fossilization. So finding bones would be hard. Finding artifacts, even harder. Stone tools last. We find hand axes from 1.5 million years ago, but those are solid stone. Simple shapes, hard to destroy. What about complex technology? Circuit boards, machinery, plastics. Plastic seems like it lasts forever, but that's on human timescales. Give it 1,000,000 years buried in sediment, pressure, heat, chemical reactions. It breaks down. Eventually, metal corrodes, circuits dissolve, glass becomes sand again, everything returns to simpler forms. There's a thought experiment scientists use. Imagine aliens visit Earth 1 billion years from now. Could they tell we were here? Maybe, if they looked carefully, but it wouldn't be obvious. They might find a thin layer of unusual materials, concentrated metals in weird places, plastic residue in sedimentary rock, radioactive isotopes that don't occur naturally, but they'd have to know what to look for, and they'd have to look in the right places. Which brings us back to the Silurian Hypothesis. How would we detect an ancient industrial civilization? Frank and Schmidt focused on chemical signatures, things that might show up in rock layers. First, carbon isotopes. When you burn fossil fuels, you release carbon that's been locked underground for millions of years. This carbon has a specific isotopic signature, different from carbon in living things. So if an ancient civilization burned coal or oil, it might leave a spike in carbon isotopes, a thin layer where the ratio suddenly changes. We do see these spikes in Earth's history, but they have other explanations. Volcanic eruptions release old carbon, so do natural climate shifts. Still, the spikes are there, and we can't always explain them perfectly. Second, temperature changes. Industrial civilization warms the planet. We're doing it right now. The geological record should show this, a sudden temperature spike, lasting maybe 100,000 years, then fading. Earth's history has these too. The Paleocene-Eocene thermal maximum happened 56 million years ago. Temperatures jumped 5 to 8 degrees Celsius in about 20,000 years. That looks like what we're doing now, but it probably wasn't a civilization. Probably. There are natural explanations. Massive volcanic activity, methane release from the ocean floor. But here's what gets me. We see the effect, we infer the cause. We can't actually prove what happened. Third, synthetic materials, plastics, certain metals, industrial chemicals, things that don't occur in nature. These would break down, but they might leave traces. Strange molecules in the rock, concentrations of elements that shouldn't be together. We haven't found anything like this, but we haven't really looked. Why would we? Until recently, nobody thought to ask the question. Fourth, mass extinction. Industrial civilization disrupts ecosystems. Species die off. This shows up in the fossil record as a sudden loss of diversity. Earth has had 5 major mass extinctions, and several smaller ones. Each has explanations: meteor impacts, volcanic eruptions, climate change. But what if some weren't natural? What if one was caused by something we can't see anymore? We'd never know. The civilization would be gone. Only the extinction would remain. This is the unsettling part. The evidence would look exactly like natural causes, because after enough time, we can't tell the difference. Frank and Schmidt weren't arguing that ancient civilizations existed. They were, pointing out that we couldn't rule them out. The absence of evidence isn't evidence of absence, not when the evidence would disappear anyway. So what's the actual probability? That something built cities millions of years ago? Probably low. Life on Earth took a long time to evolve intelligence. Billions of years. It might be rare. It might have only happened once. But we don't know that for certain. Evolution experiments with different forms. Intelligence could have emerged before, then died out, then emerged again. There were smart dinosaurs. Troodon had large brains for its size. It might have been clever. Not civilization building clever, but who knows what might have evolved if the asteroid hadn't hit? There were intelligent marine reptiles, mosasaurs, plesiosaurs. They ruled the oceans for millions of years. Could something like them have developed technology? Probably not. Tool use is hard underwater. Fire is impossible. You need certain conditions for civilization to develop, but the Earth has existed for 4.5 billion years. Life for 3.5 billion. That's a lot of time, a lot of chances. And here's the thing that keeps me curious. We're only just learning to ask these questions. We're only just developing the tools to look. What if we find something? Not proof, just a hint. An anomaly we can't explain. A chemical signature that doesn't fit. It wouldn't change everything, but it would change how we see our place in time. We think of ourselves as the first, the only, the special ones who figured out fire and tools and cities. But what if we're just the latest? What if this has happened before? The Earth would still be here, still spinning, still recycling itself, hiding its secrets in layers of stone, and we'd be one more experiment, one more attempt, one more species trying to leave a mark that won't wash away. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching, from and what time it is. I always check the comments. Anyway, back to deep time and hidden history. The Earth keeps secrets well. Too well, maybe. It buries things, melts them, grinds them into dust, every trace erased. But sometimes, just sometimes, something survives. A hint, an anomaly, a pattern that doesn't quite fit. And that's where this gets interesting. The Earth recycles. That's not poetic. It's geology. The planet has systems, processes that run constantly, breaking things down, building new things up. Nothing stays the same for long. Start with weathering. Rain falls. It's slightly acidic. Just from carbon dioxide in the air, that rain hits rock, slowly dissolves it. Year after year, century after century, granite mountains become sand, limestone cliffs become mud. Everything breaks down eventually. Then there's erosion. Wind scrapes surfaces, rivers cut valleys, glaciers grind bedrock into powder. The Grand Canyon is a mile deep. The Colorado River carved it in just 6 million years. That's nothing in geological time. 1 mile of rock gone, carried away to the ocean. Now imagine what happens to a city, a building, a road. Even made of concrete and steel, it doesn't stand a chance. Wind wears it down, rain dissolves it, plants crack it apart, roots work into every gap, freeze-thaw cycles split stone. Within a few thousand years, most of it would be rubble. Within 100,000, you'd need to dig to find anything, but erosion is just the start. The Earth has more aggressive systems, plate tectonics, the ground moves, continents drift, about as fast as your fingernails grow. Doesn't sound like much, but over millions of years, it adds up. India crashed into Asia, pushed up the Himalayas, the tallest mountains on Earth, all from continental drift. The Atlantic Ocean is getting wider, about an inch per year. Europe and North America are moving apart. In 200 million years, the gap will be twice as wide. And here's the thing, where? Continents spread apart, they come together somewhere else. Subduction zones. One plate slides under another, gets pushed down into the mantle, where it melts. The ocean floor is constantly recycling. New crust forms at mid-ocean ridges. Old crust gets swallowed at subduction zones. The oldest ocean floor on Earth is about 200 million years old. Everything older is gone, melted, recycled into new rock. So if a civilization built coastal cities 300 million years ago, the entire coastline might not exist anymore. The ocean floor it sat on could be gone, pulled under a continent, melted back into the mantle. No trace left, not because someone destroyed it, because the Earth recycled it. Then there's metamorphism. When rock gets buried deep enough, heat and pressure change it. Limestone becomes marble, shale becomes slate, sandstone becomes quartzite. The original structure is destroyed. Fossils get warped, erased. Any artifacts would be crushed, melted, transformed into something unrecognizable. And if the rock goes deeper still, it melts completely. Becomes magma. All information lost. The rock cycle works like this. Igneous rock forms from cooling magma. Weather breaks it down into sediment. Sediment gets compressed into sedimentary rock. That rock gets buried and becomes metamorphic rock. And if it goes deep enough, it melts back into magma. The cycle takes millions of years, but it's relentless. Nothing escapes it forever. Now add volcanism. The Earth's interior is hot. Molten rock pushes up through the crust, sometimes explosively, sometimes slowly. Volcanic eruptions bury things. Pompeii was covered in 79 AD, preserved under ash, but that's rare. Usually volcanic activity destroys. The heat melts things. The lava buries them under new rock, and volcanic hotspots move. The Hawaiian Islands formed as the Pacific Plate moved over a hotspot. Each island is a different age. The oldest islands are being eroded away. Eventually they'll sink back into the ocean, disappear completely. The Earth creates land, then destroys it, then creates new land somewhere else. There's also glaciation. Ice ages come and go. Glaciers a mile thick cover continents. They grind bedrock into powder, carve valleys, push boulders hundreds of miles. When the ice melts, it dumps sediment everywhere, burying whatever was there before. The Great Lakes formed from glacial erosion, just in the last ice age, which ended only 12,000 years ago. Imagine what multiple ice ages could do. Over millions of years, any surface features would be scraped away, ground into dust, scattered across continents. And we're just talking about the surface. The Earth has other ways of hiding things. Sedimentation. Rivers carry sediment to the ocean. It settles on the bottom, layer after layer, year after year. The Mississippi River dumps 500 million tons of sediment into the Gulf of Mexico every year. That sediment buries whatever's on the ocean floor, ancient coastlines, river deltas. Anything that was there gets covered, deeper and deeper. After a few million years, you'd need to drill through miles of sediment to reach it, and by then, the weight of all that sediment has compressed the lower layers, changed them, destroyed fine details. Then there's chemical weathering, not just physical breakdown, actual chemical changes. Iron rusts, copper corrodes, aluminum oxidizes, even stone dissolves in acidic water. Any metal artifacts would corrode away in thousands of years, not millions, thousands. Steel rusts quickly, bronze lasts longer but still corrodes. Gold is stable, but it's rare, and small gold objects could be scattered, lost, impossible to distinguish from natural gold deposits. What about plastics? We produce 400 million tons per year. Surely that would leave a trace. But plastics break down. Slowly, yes, but they break down. UV light from the sun makes them brittle. They fragment into smaller pieces, microplastics. Then those break down further. Over millions of years, even plastic would degrade. The carbon would be recycled, eaten by bacteria, broken down into simpler molecules. Eventually it would be indistinguishable from natural organic material. And remember, most of our plastic ends up in landfills, buried, where it breaks down even faster. Without sunlight, bacteria work on it, slowly turning it back into carbon dioxide and water. What about radioactive waste? We produce that too. Surely that would last. Some isotopes have half-lives of thousands of years, but half-life means half the material decays. After 10 half-lives, almost nothing is left, and 10 half-lives of even long-lived isotopes is still just hundreds of thousands of years, not millions. Plus, radioactive materials are often stored deep underground, in geologically stable areas, which means they're in places likely to be subducted, or buried under more sediment, or metamorphosed into different rock. The Earth doesn't preserve things, it recycles them. That's what it does, that's what it's always done. So when we ask whether an ancient civilization could leave traces, we have to understand what we're up against. Not just time, but active geological processes, working constantly, breaking things down, burying them, melting them, transforming them. The Earth is 4.5 billion years old. It has recycled its surface many times over. The oldest rocks on Earth are about 4 billion years old, and those are rare. Most of the surface is much younger, constantly being renewed. If a civilization existed 100 million years ago, most of the surface they lived on is gone now. Subducted, eroded, buried, melted, transformed. The Earth has recycled it. And that's the problem. Not that we're not looking hard enough, but that the Earth is really good at erasing history. Too good. Almost nothing survives deep time. Not cities, not roads, not even mountains. The Appalachian Mountains used to be as tall as the Himalayas, now they're rounded hills, worn down by 300 million years of erosion. Half their height is gone, just gone, carried away to the ocean. If mountains can't survive, what chance does a civilization have? Fossils are rare, way more rare than people think. We imagine dinosaur bones everywhere, museums full of skeletons, complete specimens mounted for display. But that's misleading. Those displays represent millions of years and entire continents. The actual odds of fossilization are tiny. Here's how bad it is. Less than one organism in a billion becomes a fossil. 1 in a billion. And most of those are just fragments. A tooth, part of a shell, a single bone. Complete skeletons? Those are lottery wins. Multiple lottery wins. Everything has to go right. First, the organism has to die in the right place. Usually water, lakes, rivers, oceans. The body needs to sink into sediment quickly, before scavengers tear it apart, before bacteria break it down completely. Then it needs to stay buried, undisturbed. While minerals slowly replace the organic material, this takes thousands of years, sometimes millions. But burial isn't enough. The sediment has to turn into rock. That requires pressure, more sediment piling on top, compressing the layers below. If the pressure is too much, the fossil gets crushed. Too little, and it doesn't preserve. And then, after all that, the rock has to survive. Can't get subducted under a tectonic plate. Can't get metamorphosed by heat and pressure. Can't erode away before someone finds it. Oh, and someone has to find it. The rock has to be exposed at the surface, at the exact moment when humans are looking, in the exact spot where someone happens to be digging. The odds are absurd, which is why fossils are so rare. Think about dinosaurs. They dominated Earth for 165 million years, millions of species, billions of individual animals. We found maybe a few thousand complete skeletons, total. From the entire age of dinosaurs, some species we know from a single bone. One fossil. That's it. The only proof they existed. Other species probably left no fossils at all. They lived. They died. They vanished without a trace. Now think about humans. Modern humans have existed for 300,000 years. How many complete human skeletons have we found from before 10,000 years ago? A few hundred. Maybe. The further back you go, the fewer there are. From 100,000 years ago, a handful. From 200,000 years ago, almost nothing. And these are humans, our own species. We're actively looking for them. We know what to look for. We care about finding them, and we still barely have anything. So what about a completely unknown species? Something we're not looking for, something that might not look human at all? What are the odds we'd find it? Close to zero, even if it existed. But it gets worse, because not all organisms fossilize equally. Some things preserve better than others. Shells and bones do okay. They're hard. They have mineral content already. The fossilization process works on them, which is why most fossils are shells, bones, and teeth. Soft tissue almost never preserves. Skin, muscles, organs, gone within days. Bacteria eat them. They decay. They leave nothing behind. We have thousands of dinosaur skeletons. We have maybe a dozen examples of preserved dinosaur skin. And those are exceptional cases, usually from animals that died in very specific conditions, buried in fine sediment, protected from oxygen, mineralized quickly. It's so rare that each discovery makes headlines. Now think about something without bones. Jellyfish, worms, octopi. They're everywhere today. Millions of them. But their fossil record is almost non-existent because they're soft. They decay completely. They leave nothing to fossilize. The Cambrian explosion happened about 540 million years ago. Complex life suddenly appeared. Except it probably didn't suddenly appear. It probably evolved gradually. But we can't see the earlier stages because those organisms were soft-bodied. They didn't fossilize. We only see the story once shells evolved, once hard parts appeared. Before that, the record is blank, not because nothing was there, but because soft things don't preserve. So if an ancient civilization existed, what would fossilize? Not their bodies, not if they were soft tissue, not their cities. Buildings aren't organisms. They don't fossilize, not their technology. Metal corrodes, plastic breaks down, maybe nothing at all. But let's say they had bones. Let's say they were vertebrates like us. What are the odds we'd find them? Depends on how many there were, and where they lived, and when they died. Modern humans number 8 billion. That's a lot, but we're spread thin. Most of us live in cities, coastal areas, river valleys. If civilization collapsed tomorrow, most bodies would decay in place. In environments that don't preserve fossils, you need the right conditions. Swamps, lake beds, river deltas, places where sediment accumulates, where bodies get buried quickly. Even then, you need luck. The sediment has to become rock. The rock has to survive. Someone has to find it. And remember, we're talking about millions of years, not thousands, millions. The oldest human fossils are about 300,000 years old. That's recent. Incredibly recent. Go back 10 million years, we have almost nothing, a few fragments, scattered across continents. Go back 100 million years. The fossil record is dominated by dinosaurs, because there were so many of them, for so long. And even then, we only have a tiny fraction of what existed. An industrial civilization might last a few thousand years, maybe 10,000. That's a blip, a moment. In 100 million years, that moment gets lost, buried under everything that came after. And here's another problem. We don't know what we're looking for. When we find a weird fossil, we try to fit it into what we know. We compare it to existing animals. We look for evolutionary relationships. But what if something doesn't fit? What if it's too different? We might not recognize it as artificial. We might think it's a natural formation, or a deformed bone, or contamination. There are weird fossils, things that don't quite fit. Usually there's an explanation, a misidentification, a hoax, natural processes that look artificial. But sometimes there isn't a clear answer. The fossil is just strange, anomalous, and it sits in a drawer somewhere, labelled as unknown or unclear origin. Could some of those be evidence? Maybe. Probably not, but maybe. The point is, absence of evidence isn't evidence of absence, especially when the evidence is this hard to find. We haven't found fossils of an ancient civilization, but we probably wouldn't, even if one existed. The odds are too low. The time is too long. The Earth is too good at erasing things. Dinosaurs had 165 million years, billions of individuals, and we found maybe 0.1% of species, probably less. An industrial civilization might have millions of individuals, not billions, and they might last 10,000 years, not millions. The fossil record would be almost empty, a few fragments, if anything at all. So when we ask whether an ancient civilization existed, we can't rely on fossils. They're too rare, too dependent on luck, too easily lost to deep time. We need something else, something more durable, something that would survive when bones don't. But what? If bones don't make it, what possibly could? So if physical evidence disappears, what's left? Chemistry. Chemical signatures last way longer than bones, longer than buildings, longer than almost anything. And some of them are really hard to explain naturally. Think about what an industrial civilization does. It burns things. Coal, oil, gas, all that burning releases carbon dioxide. But not just any carbon dioxide, a specific type. Carbon comes in different versions. isotopes. Carbon-12 is the common one. Carbon-13 is heavier. Both are stable. Both occur naturally. But here's what matters. When you burn fossil fuels, you release carbon that's been locked underground for millions of years. Old carbon has a different isotope ratio than modern carbon. Plants prefer lighter carbon. Carbon-12, when they photosynthesize, they pull in more carbon-12 than carbon-13. That preference shows up in the plant tissue. When plants die and turn into coal or oil, that ratio stays locked in. Millions of years later, when you burn that coal, you release carbon with an unusual isotope signature. Less carbon-13 than you'd expect. More carbon-12. That signature spreads through the atmosphere, gets absorbed by oceans, taken up by new plants, incorporated into sediments, and it shows up in the rock record, a spike, an anomaly, a layer where the carbon ratios shift suddenly. We can measure this. Scientists drill ice cores, ocean sediments, rock layers. They analyze the carbon, isotopes in each layer, build a timeline going back millions of years, and when they see a sudden shift in carbon ratios, they know something happened. Something released a lot of old carbon. Fast. Right now, we're creating that signature. Our industrial civilization burns fossil fuels at an incredible rate. About 10 billion tons of carbon per year. That carbon spreads everywhere. Future geologists will see it clearly, a sharp spike in the carbon record, starting around 1850, getting steeper every decade. They'll know something burned a lot of old carbon. They might not know what, but they'll see the signature. So here's the question. Are there other spikes? Other anomalies in the carbon record? Times when the ratio shifted suddenly for no clear reason? Yes. Several. Some have explanations. Volcanic eruptions release carbon. So do asteroid impacts. Natural events that pump carbon dioxide into the atmosphere. But volcanoes and asteroids have other signatures too. Iridium, layers, shocked quartz, ash deposits. You can tell what caused them. Other spikes are harder to explain. The carbon ratios shift, but there's no obvious natural cause. No volcano, no impact, just a sudden change in atmospheric chemistry. Could those be industrial civilizations? Maybe. Probably not, but maybe. The problem is time. These spikes happened millions of years ago. The details are fuzzy. The rock record is incomplete. We're looking at averages across thousands of years. Our current industrial spike will look sharp in the record. It happened fast. Over 200 years. That's nothing geologically, but compress it down to a thin layer in the rocks. Smear it across thousands of years of sedimentation. It might not look that different from a volcanic event, or a period of intense forest fires. Still, the carbon signature is one of the best candidates for detection. It lasts. It spreads globally. It's measurable. But there are other chemical signatures too, some even stranger. Plastics, for example. We make about 400 million tons of plastic every year. Most of it doesn't biodegrade. Not quickly anyway. Plastic breaks down into smaller pieces, microplastics, nanoplastics. But the polymers themselves stick around. They're synthetic. Nature doesn't have good tools to break them down, so plastic accumulates. In oceans, in soil, in sediments. Eventually it gets buried, compressed into rock layers. Future geologists might find a thin layer of plastic-rich sediment, a marker horizon, proof that something made synthetic polymers. That's pretty hard to explain naturally. Plastics don't occur in nature, not these kinds. If you find them in the rock record, something made them. Same with certain metals. Aluminum, for instance. Pure aluminum doesn't exist naturally. It's always bound up in minerals, bauxite, clay. To get pure aluminum, you need electricity. A lot of it. You have to smelt the ore, extract the metal through electrolysis. If you find pure aluminum in ancient rocks, that's weird. Really weird. It suggests smelting, refining, technology. We haven't found that, but if it existed, it would be a smoking gun. Then there are the really exotic signatures, radioactive isotopes that don't occur naturally. Plutonium-239, for example. It only exists if you make it in a nuclear reactor. If you find plutonium-239 in ancient sediments, that's not natural. Can't be. It means someone was splitting atoms. We've tested for this. Scientists have analysed ancient rocks for unusual isotopes, looking for signs of ancient nuclear reactions. So far, nothing. No plutonium, no enriched uranium, no fission products. But there is one natural nuclear reactor, Oklo, in Gabon. About 2 billion years ago, uranium deposits there went critical, started a chain reaction, ran for hundreds of thousands of years. It happened naturally. The uranium concentration was high enough. Water acted as a moderator. The conditions were just right. When scientists found it, they were confused. The isotope ratios were wrong. Too much of certain elements, not enough of others. Eventually they figured it out. Natural fission, no technology required, just geology and luck. So even weird isotope ratios aren't proof of technology. Nature can do strange things. But combine multiple signatures, that's harder to explain away. Carbon isotope spike plus plastic polymers, plus refined metals, plus radioactive isotopes, all in the same layer, all at the same time. That would be compelling. That would be hard to dismiss as natural. We haven't found that combination. Not yet. But we're not really looking, not systematically. Most geological surveys focus on resources, oil, minerals, understanding past climates. Nobody's specifically searching for ancient industrial signatures. Maybe they should be. Because here's what gets me. We know chemistry lasts. We know it spreads globally. We know it's detectable. If someone burned fuel 100 million years ago, we might see it. If they made plastics, we might find them. If they refined metals, traces could remain. The signatures are there. If the civilizations were there, and there's one more chemical signature, one that's really hard to explain, one that shows up in the geological record with no clear natural cause. Nitrogen isotopes, specifically the ratio of nitrogen 15 to nitrogen 14. Fertilizer production changes this ratio. Industrial agriculture uses synthetic nitrogen, made through the Haber-Bosch process. That process has a specific isotope signature. When you spread that fertilizer on fields, it washes into rivers, flows to oceans, gets incorporated into marine sediments. Future geologists will see it. A shift in nitrogen ratios, starting in the early 1900s, growing exponentially. Are there similar shifts in the past? Times when nitrogen ratios changed suddenly? Yes, several times, usually explained by changes in ocean circulation or shifts in the nitrogen cycle. Natural processes, but some are harder to explain. The timing is odd, the magnitude is strange, the pattern doesn't quite fit. Could those be agriculture, industrial scale farming, synthetic fertilizer? Probably not, almost certainly not. But the question is interesting, because chemistry doesn't lie. It records what happened, even if we don't understand it yet. And here's the thing. We've already found a suspicious spike in the ancient record, the PETM, the Paleozoic-Eocene thermal maximum. About 56 million years ago, something happened. The planet heated up, fast. Global temperatures jumped by 5 to 8 degrees Celsius. In geological terms, that happened overnight. Maybe 20,000 years. Sounds like a long time, but in deep time, it's a blink. The oceans warmed, ice caps melted, sea levels rose, species went extinct, others migrated, the whole planet shifted, and in the rock record, there's a spike. Carbon isotopes. The ratio changed suddenly. more carbon-12, less carbon-13, exactly the pattern you'd see from burning fossil fuels. Scientists have studied the PETM extensively. They've drilled cores, analysed sediments, built models, tried to figure out what caused it. The leading theory involves methane, massive amounts of methane trapped in ocean floor sediments, methane hydrates, frozen methane locked in ice. Something triggered a release. Maybe volcanic activity, maybe warming oceans. The methane bubbled up, hit the atmosphere. Methane is a powerful greenhouse gas, much stronger than carbon dioxide. The methane caused warming. The warming released more methane, a feedback loop, runaway heating. Eventually the methane oxidized into carbon dioxide. That carbon spread through the atmosphere, got absorbed by oceans, incorporated into sediments, and that's what we see. A carbon spike, a warming event, mass disruption of ecosystems, natural causes, no civilization required. But Frank and Schmidt looked closer. They asked a different question. Could you tell the difference? If an industrial civilization caused the PETM instead of methane, would we know? The answer is uncomfortable, maybe not. Both scenarios produce similar signatures. Carbon isotope spikes, global warming, ocean acidification, species extinction. The timescales blur together. 20,000 years of industrial activity would look similar to a methane release, especially after 56 million years of geological processing. You'd need additional evidence, multiple signatures, not just carbon, other chemicals, synthetic materials, refined metals, and that's where it gets tricky. Because we haven't looked. Not really. Not systematically. Most studies of the PETM focus on climate, ocean chemistry, species extinction, understanding natural processes. Nobody's checking for plastic polymers in PETM sediments. Nobody's analysing for refined aluminum. Nobody's searching for artificial isotopes. Why would they? The methane hypothesis explains everything. It fits the data. It makes sense. But absence of evidence isn't evidence of absence, especially when you're not looking. Schmidt and Frank aren't claiming the PETM was caused by civilization. They're not saying ancient reptiles burned coal 56 million years ago. They're making a different point. We don't actually know how to detect ancient industrial civilizations. We haven't developed the methods. We haven't done the surveys. If one existed, we might miss it. Even if the evidence is sitting in museum collections right now, think about that. Rock samples drilled from PETM layers, sitting in storage, analysed for certain things, but not others. What if someone tested those samples for synthetic polymers, for refined metals, for isotopes that shouldn't exist naturally? Would they find anything? Probably not, almost certainly not. But the question is worth asking, because chemistry doesn't lie. It records what happened. And there are other anomalies in the geological record, other carbon spikes, other warming events, some explained, some less clear. The torsion turnover, about 183 million years ago, during the Jurassic period, massive volcanic eruptions, carbon spike, ocean acidification, mass extinction, clearly volcanic. The evidence is everywhere. Flood basalts, ash layers, shocked minerals. But the carbon spike is interesting. It's sharp, concentrated, happens faster than the volcanic activity alone would suggest. Maybe there's another mechanism, something that amplified the volcanic warming, released additional carbon, methane again probably, or massive wildfires. Natural explanations exist, but you could fit an industrial civilization in there, hypothetically, if you wanted to, if the evidence supported it. Nobody's checked, because why would you? The volcanic explanation works. Then there's the Permian-Triassic boundary, the Great Dying. 252 million years ago, the worst extinction event in Earth's history. 96% of marine species gone, 70% of land species. The planet nearly sterilized. The cause? Volcanic activity. The Siberian traps, massive eruptions that lasted millions of years, released enormous amounts of carbon dioxide and sulfur dioxide. The carbon spike is huge, unmistakable, and the volcanic evidence is clear. But the extinction happened in pulses, multiple waves. Some species died quickly, others lingered. The pattern is complex. Could there be additional factors? Something else contributing to the collapse? Scientists have proposed many mechanisms: ocean anoxia, acid rain, ozone depletion, hydrogen sulfide poisoning, all natural, all plausible, all supported by evidence. But again, nobody's specifically looking for industrial signatures, synthetic chemicals, refined materials, artificial isotopes. The volcanic explanation is sufficient. No need to look further. And that's the point Frank and Schmidt are making. We're not looking. We don't have protocols. We don't have baselines. If we wanted to search for ancient industrial civilizations systematically, we'd need to develop new methods, new tests, new ways of analyzing old samples. We'd need to know what to look for, what chemicals would survive, what concentrations would be detectable, what patterns would be unmistakable. Right now, we don't have that knowledge. We're flying blind. But there's one signature that might work, one chemical marker that's hard to fake, hard to explain naturally: nitrogen isotopes. Specifically, the ratio of nitrogen 15 to nitrogen 14 in marine sediments. Industrial agriculture changes this ratio. Synthetic fertilizer made through the Haber-Bosch process has a distinctive isotope signature. When you spread fertilizer on fields, it washes into rivers, flows to the ocean, gets incorporated into marine organisms, eventually settles into sediments. Future geologists will see it clearly, a shift in nitrogen ratios, starting in the early 1900s, growing exponentially through the 20th century. That signature is hard to explain naturally. Nitrogen cycles are complex, but they're usually stable. Dramatic shifts require something unusual. Volcanic activity can change nitrogen ratios, but volcanoes have other signatures. You can tell. Changes in ocean circulation affect nitrogen, but those changes are gradual, not sharp spikes. Industrial agriculture is different. It's sudden, concentrated, unmistakable. So if you found a sharp nitrogen isotope spike in ancient sediments, with no volcanic or circulation explanation, that would be interesting. Really interesting. And there are anomalies, times when nitrogen ratios shifted suddenly. Most have explanations, natural processes, changes in ocean chemistry, but some are puzzling. The timing is odd, the magnitude is unusual, the pattern doesn't quite fit standard models. Could those be agriculture? Industrial-scale farming from ancient civilizations? Almost certainly not. The natural explanations are more likely, much more likely, but the question lingers. Because we're not looking systematically. We're not testing specifically for industrial signatures. We're studying past climates, understanding natural cycles, not searching for lost civilizations. And maybe that's fine. Maybe there's nothing to find. Probably there's nothing to find. But Frank and Schmidt have shown something important. We wouldn't necessarily know. Even if the evidence exists, we might not recognize it. The geological record is incomplete. Our methods are limited. Our assumptions are strong. We assume natural causes until proven otherwise. That's good science. That's how it should work. But it means we might miss things. Anomalies that don't fit. Patterns that suggest something else. The PETM carbon spike looks industrial, but we explain it naturally. Methane release, volcanic activity, feedback loops. And we're probably right. almost certainly right. But what if we're not? What if there's a thin layer of synthetic polymers in those sediments? What if there are refined metals we haven't tested for? What if the isotope ratios tell a different story when you look closer? We won't know unless we look, and right now we're not looking. Because chemistry lasts. It spreads globally. It records what happened. Even when everything else is gone, even when the cities are dust and the bones are dissolved and the continents have drifted, the chemistry remains, waiting, patient, ready to tell its story if we learn how to read it, if we develop the methods, if we ask the right questions. The signatures are there, locked in ancient rocks, preserved in sediment layers, spread across continents. All we have to do is look, really look, with new eyes and new tools and new questions, and maybe, just maybe, we'll find something that changes everything we thought we knew about deep time and hidden history. Or maybe we'll confirm what we already believe, that we're the first, the only, the beginning of something new. Either way, the chemistry will tell us, if we listen. So, what would actually survive? What chemicals, plastics, or metals could last through all the grinding, melting, and burying that the planet puts everything through? Let's break it down, one clue at a time. First, let's talk about plastics. Right now, we make over 300 million tons of plastic every year. Bags, bottles, wrappers, so much that you can find it in every ocean, even at the bottom of the Marianas Trench. Plastics don't break down like food or wood. Instead, they break into smaller and smaller pieces called microplastics. These are everywhere. Sand, water, even the air. But would plastic last for millions of years? That's the real question. Most plastics break down in sunlight, thanks to a process called photodegradation. Sunlight hits a plastic bottle, and over time, the bonds between the atoms break apart. The bottle turns brittle, then cracks, then crumbles into tiny pieces. Wind blows the pieces around. Rain washes them into rivers. Eventually they end up in the ocean or get buried in new layers of dirt. But here's the twist. If plastic gets buried deep enough, quickly enough, like in a mudslide or under the silt at the bottom of a lake, it's safe from sunlight. No UV rays, no breaking down. Just slow decay, if any. Some scientists think that, in the right conditions, plastic could last for hundreds of thousands of years, maybe longer if it's buried deep and undisturbed. Now, imagine a civilization even half as plastic crazy as we are. If they dump their trash into landfills, rivers, or oceans, some of it might get buried and survive. Not whole bottles or bags, those would be smashed and flattened, but little bits, fragments, microplastics in layers of mud and clay. Fast forward to the present. Geologists drill a core from the ocean floor. They see a layer with thousands of tiny plastic bits, maybe even fibers from old clothes. If you found that 100 million years from now, you'd know something strange happened. Nature doesn't make plastic, it's a human fingerprint. But there's a catch. Over deep time, heat and pressure could change plastic into something else. Maybe it turns into a waxy substance. Maybe it breaks down completely, leaving only a weird chemical signature behind. Detecting it would be hard, especially if you don't know to look for it. Next, let's talk about metals. We use tons of metal: aluminum, copper, steel, gold. Some metals, like gold, are pretty stable. They don't rust or break down easily. Others, like iron, rust quickly and vanish. But almost all metals we use are refined. We take ores from the ground, then use fire and chemicals to purify them. The result is metal that's way more pure than you'd ever find in nature. So, could future scientists spot metal from an old civilization? Maybe. If you found a chunk of pure aluminum in a rock layer from 200 million years ago, you'd have questions. Same with copper wire or a piece of stainless steel. But these metals don't just sit around. Over time, they corrode, mix with other elements, or even melt if the rock gets hot enough. Still, traces might survive. For example, aluminum doesn't occur in pure form naturally. You have to make it. So, if someone found pure aluminum in an old sediment layer, that would be a smoking gun. But nobody has. At least, not so far. What about glass? We use glass for everything. Windows, bottles, screens. Glass is just melted sand. But the stuff we make is different from what forms naturally, like obsidian. Ancient glass can last thousands of years, even in harsh conditions. Sometimes, Roman glass beads are dug up after 2,000 years and still look almost new. Glass is tough, but not unbreakable. It cracks, it weathers, it gets cloudy. Over millions of years it would likely dissolve, especially in wet places. Still, some glass might survive if it was buried deeply and kept dry. Maybe not in perfect shape, but tiny fragments fused with other minerals could last much longer. If you dug up a strange layer of glass beads or melted glass, far older than any known civilization, that would be weird. But glass is tricky. Volcanic eruptions also make glass. Lightning strikes sand and creates glassy tubes called fulgurites. So, you'd need more than one clue to say for sure. Now, let's think about chemicals. Some chemicals are made only in labs or factories. PCBs, for example, are a kind of oil used in electronics and coolants. They don't occur naturally. PCBs are stable and can last a long time in soils and sediments. Scientists have found PCBs in the fat of whales and polar bears. They even show up in the Arctic, far from any factory. Suppose another civilization used chemicals like this. Maybe not PCBs exactly, but something just as strange. If those chemicals got into the ocean or soil, they could end up trapped in mud or clay. Even after the buildings were gone, even after all the bones had dissolved, those molecules might still be there. Scientists today can find single molecules in ancient sediments. If you looked for the right thing, you might find a chemical nobody can explain. And this is where it gets really interesting. Nuclear power. Our reactors make elements that don't exist in nature. Plutonium, americium, isotopes with weird numbers of neutrons. Some of these decay fast, but others can last for millions of years. If you buried nuclear waste deep underground, some of it could last almost forever. At least in geological terms. If a civilization used nuclear power, or even just tested nuclear bombs, they'd leave a mark. Fallout from bomb tests spreads around the world. It settles in soil and ice. It makes tiny glass beads called trinitite. It changes the balance of radioactive elements in rocks. Even after 100,000 years, some of those changes would still be there. If you found a layer rich in rare isotopes, things like plutonium or cesium-137, in a rock that's way too old for humans, you'd have to ask questions. Did a supernova spray the Earth with cosmic dust? Or did someone split atoms long before us? But as clever as these signals are, the planet is a tough place for evidence. Everything gets mixed, buried, or melted. Even nuclear waste can get pulled down into the mantle or recycled by moving plates. Let's talk about fossil fuels. If a civilization burned coal or oil, they'd release certain chemicals. Mercury is one. Burning coal releases mercury vapor into the sky. It falls as rain, then settles into mud and lakes. Over time, these layers build up. Scientists can see spikes in mercury that match modern coal burning. Now, volcanoes also release mercury, so you'd need to separate out natural events from anything artificial. But if you saw a sudden global spike in mercury, along with other weird chemicals like lead from gasoline, that might be a clue. Lead is another story. For decades, we put lead in gasoline. It spread everywhere. Oceans, soils, even inside our own bones. If you measure ice cores in Greenland, you can see when we started and stopped using lead. It's a perfect marker for our time. No natural process puts that much lead into the atmosphere all at once. What about synthetic fertilizers? As we talked about before, the nitrogen isotope ratio changes with industrial farming. This is a modern marker, but it's hard to see how nature could do the same thing so quickly, on such a huge scale. Now let's think about concrete. Modern concrete is everywhere. Roads, buildings, dams. It's made by mixing limestone, clay, sand and water, then heating it up. The Romans used concrete, and their structures are still standing after 2,000 years. But concrete does break down. Water gets in, freezes, cracks it apart. If a huge amount of concrete got buried by a landslide, could it last? Maybe. It might turn into a weird kind of rock if you found a layer full of crushed, cemented stone with shapes that don't match natural rocks. You might wonder. But nature makes concrete too. Some ancient reefs, called stromatolites, are made by bacteria and minerals. They look a bit like concrete, so once again, you'd need more than just a strange rock. You'd need a pattern, materials, chemicals, and shapes all pointing the same way. Let's talk about city layouts. If you could see a city from above, you'd notice grids, roads, and squares, straight lines. Nature prefers curves. Rivers meander, roots twist. Cities are all about order, blocks, circles, rectangles. If a city lasted long enough and got buried, could you find its shape? Maybe. Some ancient cities, like those in Mesopotamia, are now just faint marks on the land. In satellite photos, you can see the shadows of lost streets and walls. But after millions of years, even those marks would fade. Tectonic plates would crush and stretch the surface. Erosion would smooth everything out. Maybe, just maybe, if you had the right technology, you could spot something odd deep underground. A circle here, a straight line there, but that's a long shot. What about mining? Our mines are huge. Open pit mines are visible from space. They leave scars, giant holes, piles of waste rock, tailings ponds full of chemicals. Deep mines leave tunnels and shafts. If another civilization dug for minerals, they'd leave scars too. But over time, landslides would fill the holes. Rivers would wash away the waste. Only the deepest tunnels might survive, and even those could collapse or fill with minerals. But the rocks would be changed. If you analyze the minerals, you might find chemical patterns, metals in places they shouldn't be, strange mixes of elements. Some modern mines leave behind rocks with odd combinations, high copper, low iron, or rare earth metals. If you found such a pattern in the deep past, you'd start to wonder. Let's not forget about climate. Our fossil, fuel burning changes the climate, warms the planet, melts ice, raises sea levels, makes storms worse. But as we've seen, natural events can do the same thing. Volcanic eruptions, methane bursts, asteroid impacts. So, the trick is looking for combinations. A sudden spike in carbon isotopes, plus mercury, plus plastic, plus artificial chemicals. One clue isn't enough. You need a bundle of evidence, a set of markers that all point to something unnatural. Now, let's think about the fossil record itself. We know fossils are rare, but sometimes mass extinctions leave a special kind of layer. It's called a boundary clay. Thin, dark, rich in certain elements. Sometimes these layers have tiny glass beads, or spikes in iridium, or bits of soot. If a civilization wiped itself out, say, in a nuclear war or by poisoning the air, you might see a layer like that. Lots of dead things, charcoal, soot, polluted mud, all in one place. But again, volcanoes and asteroids can do the same thing. So, scientists have to ask, is there anything that only factories or technology can make? The answer is yes, but it's rare. Some isotopes, some chemicals, some plastics. Not many, but a few. And then there's DNA. Right now, we're changing the DNA of plants and animals. Genetically modified crops feed billions. If you found a fossilized seed with a DNA code that couldn't happen naturally, that would be wild. But DNA breaks down fast. It doesn't last long in rocks. Maybe 1 million years tops, and usually much less. But what about fossils of animals with weird shapes? Suppose you found a bone that didn't fit any natural pattern, like a cow with 8 legs, or a chicken with glowing feathers. That would be hard to explain, but so far all fossils fit the tree of life. No strange creatures out of left field. Let's talk about energy. Our power plants produce heat, waste, and sometimes radioactivity. If you looked at ancient rocks and found a sudden increase in heat-altered minerals, you might wonder, but lightning, volcanoes, and asteroid impacts can all heat rocks too. You need context. Now, about timeline markers. Our civilization leaves a clear line in the rocks. It's called the Anthropocene. Plastics, metals, pesticides, concrete, and nuclear fallout, all packed into a thin layer. If you could rewind time and look at older rocks, would you see a similar line? So far, no. The planet has big changes, but nothing with our exact fingerprint. But that doesn't mean it's impossible. Maybe we haven't looked in the right place, or with the right tools. Maybe there's a layer somewhere, deep under the sea or locked in old rocks, that tells a different story. And that's what keeps scientists curious. The clues are tiny, the evidence is scattered. But chemistry remembers, even when everything else is gone. So, what would it take to prove a past civilization existed? You'd need a smoking gun, something impossible to explain by volcanoes, impacts, or natural processes. Pure aluminum, manufactured plastic, synthetic isotopes, a bundle of clues stacked together. But the planet is good at hiding things. Most evidence is lost, recycled, or buried. We could walk right past the proof and never know. Still, the search goes on. Geologists keep drilling, testing, and wondering. Maybe someday someone will find a bit of plastic or a drop of oil or a strange isotope in an old rock. And it'll make them stop and think. Was this made by nature, or by something with hands and tools long before us? It's a mystery, one that might never be solved. Or maybe, with the right questions and the right tools, we'll find the answer. For now, the best evidence is what's missing. No clear markers, no weird chemicals, no impossible metals, just the slow story of a planet that changes everything given enough time. But people are starting to look. More tests, new ideas. Maybe one day the rocks will talk. And that's the real legacy of the Silurian Hypothesis. It's not about lizard people or lost cities. It's about asking questions, learning how to see what's hidden, wondering what else might be out there, waiting to be found. So if a civilization could have existed, who might they have been? Let's look at the candidates. So let's talk about the main suspects. If we're asking who could have built an earlier civilization, almost everyone starts with the dinosaurs. It makes sense. They ruled the planet for a long time, way longer than humans have even existed. Some of them were huge, some small, some smart, some not so much. But could any dinosaur have built cities, or used tools, or made anything close to technology? First, let's be clear. Most dinosaurs were nothing like the ones in movies. Many were small, chicken-sized, or even smaller. Some were plant-eaters, others ate meat. Their world was busy, crowded, and full of danger. But when people imagine dinosaur civilizations, they usually picture big, smart predators, maybe a raptor or something similar, walking on 2 legs with sharp eyes and clever hands. Let's unpack that. Dinosaurs started out as simple creatures. Over time, they split into many groups. Some became the giant, long-necked sauropods. Others became armoured tanks like Ankylosaurus. But the ones we're most interested in are the group called theropods. These were the 2-legged meat-eaters. Think T-Rex, but also smaller ones like Velociraptor, Troodon and others. Why focus on theropods? They walked on 2 legs. Their front limbs were free, not needed for walking. Some had grasping hands, 3 fingers, claws, the ability to grab. That's important for tool use. Apes, after all, became tool makers because their hands were free. Theropods also had forward-facing eyes. That gives depth perception, good for hunting, but also for working with objects. So, is there any real evidence for a smart dinosaur? There's one name that always comes up, Troodon. Troodon was a small bird-like predator. It lived about 75 million years ago. It wasn't the biggest or the scariest, but it was one of the smartest, at least by dinosaur standards. How do we know? Scientists look at something called the encephalization quotient, or EQ. It's a fancy way of comparing brain size to body size. Humans have a huge EQ. Chimps have a pretty big one. Most dinosaurs had tiny EQs, brains the size of walnuts or even smaller. But Troodon's brain was much larger for its size. If you compare, its EQ was about 6 times higher than most other dinosaurs. Now, Troodon's brain was still small compared to a crow or a monkey, but it was big for a dinosaur. Some scientists have even called it the dinosaur Einstein. Its eyes were huge, probably good for seeing at night. Its hands were flexible, with 3 fingers. The middle finger was especially long and strong, maybe for holding prey, maybe for poking at things. Let's imagine for a second. What if Troodon had kept evolving? If the asteroid hadn't hit and the dinosaurs kept going, could Troodon's descendants have gotten even smarter? Maybe grown bigger brains, developed language, or even started using tools? This idea isn't new. In the 1980s, a paleontologist named Dale Russell made a famous model. He took Troodon, stretched its body upwards, gave it bigger eyes, a larger head, and more upright posture. The result looked almost like a human-lizard hybrid. He called it the dinosauroid. It had hands, a big brain, even an imagined language. Russell knew it was speculation, just a thought experiment, not real evidence. But it made people wonder what evolution could do, given enough time. But let's get back to reality. What do fossils actually show? There's no sign that Troodon or any other dinosaur made tools. No dinosaur fossils have been found with stone blades, shaped wood, or anything like a fire pit. No dinosaur villages or organised burials, just bones, eggs, and sometimes nests. Some experts point out the tool use leaves marks. If a dinosaur used stone tools, there'd be piles of sharp rocks or marks on bones showing they'd been cut. With humans, we see these all over. Stone flakes, butchered animal bones, fire pits, even art on cave walls. With dinosaurs, there's nothing like that. Not even a hint. But, and this is important, the fossil record is spotty. Tiny things are hard to find. Wood, skin and feathers rot away fast. If a dinosaur used sticks or leaves, we'd probably never know. Maybe they built nests or dug holes or even played with objects, but with no lasting evidence, it's hard to say. What about brains? Did any dinosaur have the kind of brain needed for planning, memory or even imagination? Bird brains give us a clue. Birds are living dinosaurs after all, and some birds are incredibly smart. Crows use tools. Parrots can talk and solve puzzles. Even pigeons can remember hundreds of pictures and patterns. Birds don't have big, wrinkly brains like mammals. Their brains are shaped differently, more compact. But they can do amazing things with what they have. So, could a dinosaur have reached bird-level intelligence? Maybe. Troodon was getting close, but there's no sign it reached the level of crows or parrots. Another thing to consider, hands. Most dinosaurs had fingers, but not like ours. Even the best, like Troodon or Velociraptor, had stiff wrists and curved claws. Good for grabbing, not so good for fine work. Birds have beaks, which are great for pecking, but not for building or shaping objects. Monkeys and apes can pick up tiny things, turn them over, and use them in clever ways. That's a big leap from claws or beaks. Let's talk about language. Humans use speech to share ideas, plan, and teach. Parrots can mimic sounds, and some can even use simple words. But no bird and no dinosaur seems to have had complex language like us. Maybe they had calls or signals. Maybe different sounds meant different things. But writing, stories, science, there's no sign. Now let's look at lifespans. Dinosaurs grew fast. Most didn't live long lives. A big dinosaur, like a T-Rex, might have lived 20 or 30 years. Smaller ones, maybe less. With short lives, it's hard to pass on knowledge. That's why humans teach their kids, who teach their kids, and so on. Culture builds up. If you only live a few years, there's less time to learn and invent. But what about birds? Some birds live a long time. Parrots can live 50 years or more. Crows and ravens can live decades. They learn from their parents. They remember faces and solve problems. That gives us a window into what's possible, even with a small brain. Let's not forget about climate and environment. The time of the dinosaurs was hot, wet, and full of plants. There were no ice caps, no frozen poles. Forests covered most of the land. Swamps and rivers were everywhere. That's good for growing bodies, but not for making fire. Wet wood doesn't burn well. Fire is a huge deal. It's how humans cook, make tools, and shape metal. If dinosaurs couldn't make fire, that limits what they could do. Could dinosaurs have used fire? There's no sign, no burnt bones, no charred wood, no ash layers that match dinosaur times. Fire might have been rare, or maybe not useful to them. Even today, very few animals use fire. Some birds in Australia seem to spread wildfires by dropping burning sticks, maybe to chase out prey, but that's about it. Let's talk about social life. Some dinosaurs lived in groups. Duck-billed dinosaurs, for example, seem to have travelled in herds. Some built nests together. That's a start. Social animals can share knowledge, work together, and protect each other. But there's no sign of organised societies, no homes, no shared food storage, no group hunting plans like wolves or chimps. Now, what about the timeline? Dinosaurs lasted a long time, way longer than humans have been around. If you lined up all of dinosaur history, it's like stacking all of human history 700 times. That's a lot of chances for something unusual to happen. But if a smart dinosaur ever did appear, it would still need the right environment. Dry land, safe shelter, food, and maybe a way to shape the world around it. And even if that happened, the odds of leaving clear evidence, something we'd find today, are tiny. Some people wonder if intelligence always leads to technology. Maybe not. Octopuses are smart, but they don't build cities. Dolphins solve puzzles, but they don't make tools. Maybe some Troodon-level dinosaur was clever, but never invented anything lasting. Intelligence doesn't always mean hammers and wheels. Here's a strange thought. Maybe there was a hidden culture, a group of smart animals that communicated, played, or even made art, but used things that don't last. Songs, dances, patterns on skin. Stories told by gesture or sound. All of that would disappear without a trace. Let's look at birds again. Some birds build incredible nests. Bowerbirds make sculptures out of sticks and decorate them with flowers, berries, even shiny trash. They do this to attract mates. The nests are complicated, sometimes with tunnels and arches. But after a few weeks, the nest falls apart. The bird moves on, the art is gone. Maybe a dinosaur made something like that. Maybe for one summer, on a quiet lake shore, a group of Troodon built strange shapes out of sticks or leaves. Maybe they showed off, danced, or played games, But when the rains came, it all washed away. Nothing left but a memory. Some paleontologists wonder if evolution could have pushed dinosaurs further, given more time. If the asteroid hadn't struck, maybe the cleverest dinosaurs would have kept getting smarter. Maybe, after another 50 million years, they'd have brains like crows or even monkeys. But that didn't happen. The asteroid wiped the slate clean. So does any of this mean an earlier civilization is likely? Not really. There's no strong evidence. No tools, no art, no fire pits, no permanent homes. Just some smart animals doing their best to survive. But the door isn't fully closed. The fossil record is full of gaps. Maybe we just haven't looked in the right place, or maybe the clues vanished before we got here. Let's talk about what it would actually take for a dinosaur to build a civilization. You'd need dexterous hands or something similar for shaping objects, a brain big enough for planning, memory and creativity, long lifespans so parents could teach their young, social groups to share ideas and work together, some way to control fire or another method for shaping materials. Birds meet a few of these requirements. Some dinosaurs were on their way, but the full package, as far as we know, that never happened. There's another theory. Maybe intelligence isn't the end goal of evolution. Maybe it's just one path out of many. Dinosaurs were incredibly successful for a long time, without ever building a city or lighting a fire. Maybe they didn't need to. Maybe survival, not invention, was the main game. Still, let's imagine a world where the asteroid missed. Forests keep growing, rivers keep flowing, and Trudon slowly evolves. Maybe one day, a Trudon descendant learns to shape a stick, then a stone. Maybe it discovers that dry wood can make a spark. Maybe after millions of years, a new civilization starts to rise. But in our world, that's not what happened. The asteroid hit. The world changed. Mammals took over. Eventually, humans appeared. We're the ones who built cities, made tools, and asked these strange questions. But dinosaurs do leave a legacy. Birds are everywhere. Parrots and crows solve problems, remember faces, and even use tools. That's a hint at what might have been. Intelligence isn't just a human thing. Nature tries out ideas all the time, so if you're looking for a lost civilization, dinosaurs are the usual suspects. The evidence isn't strong, but the idea is fun to think about. What if, somewhere in the deep past, a clever dinosaur picked up a stick, looked at the stars and wondered about its own world? Maybe it happened. Maybe not. What about other animals? Mammals were around during the time of the dinosaurs, but they were small and mostly lived in the shadows. After the asteroid, they spread and grew. Some became whales, some elephants, some apes. But as far as we know, no mammal built anything complex until humans came along. So, if dinosaurs aren't the answer, and mammals weren't ready, could something else have tried? Maybe reptiles, maybe birds, maybe something we haven't even imagined. But without clear proof, tools, fire, writing, it's just a story. Scientists keep looking. Every year, new fossils are found. New ideas are tested. The story keeps changing. Maybe someday someone will find a jawbone with tool marks, or a fossilized nest with strange shapes, or something even stranger. But for now, the story of smart dinosaurs is mostly a what-if. A mystery, open at the edges. No final answer, just questions, and the thrill of wondering. And that leads to another puzzle. Dinosaurs lived on land. But what about the ocean? That's where things get really interesting. So, we've talked about what it would take for a land animal to build something like a civilization. Hands, brains, social lives, maybe fire. But what if we look somewhere else? What about the ocean? That's a whole different world. And this is where it gets really interesting. The ocean covers more than 70% of the planet. It's deep, dark and cold in most places. We know less about the bottom of the sea than we do about the surface of Mars. For most of Earth's history, the ocean was the main stage. Life began there. For billions of years, every living thing was underwater. Now, when people think about lost civilizations, they picture land, cities, roads, ruins poking out of the jungle. But if anything strange happened in the ocean, we'd probably never find it. The sea is good at hiding secrets. Sand, silt, and mud bury anything that falls to the bottom. Currents move things around. Even shipwrecks from just a few hundred years ago are hard to find. So, let's ask a wild question. Could a civilization have evolved in the ocean? Not on the land, not in the trees, but underwater. Before you laugh, let's look at the facts. First, who are the smartest animals in the ocean? Two groups stand out: dolphins and whales and cephalopods. Cephalopods are the group that includes octopuses, squids, and cuttlefish. They're weird. No bones, soft bodies, arms covered in suckers. But here's the thing. They're incredibly smart. Let's start with octopuses. They can solve puzzles, open jars, escape from tanks, and even recognize individual people. Some scientists call them aliens on Earth. Their brains are nothing like ours. For one thing, most of their neurons, the cells that make up a brain, aren't even in their heads. 2/3 are spread out in their arms. Each arm can move, feel, and even taste on its own. Octopuses change colour and texture in an instant. They can blend into rocks, sand, or coral. Some use shells or coconut halves as tools. They pile things up to make a safe spot. There's a famous video of an octopus stacking rocks to block the entrance to its den. That's planning and problem solving. Cuttlefish, another cephalopod, can remember things they learned as babies. They watch other animals and copy their tricks. Even squids, which live in large groups, show signs of teamwork and learning. But do any of them build things that last? Not really. There are no octopus cities, no underwater roads or stone carvings. Most of what they do is temporary. They hide, they hunt, they play tricks, but almost nothing survives after they're gone. So why hasn't anything like a cephalopod civilization appeared? Let's break it down. First, life in the ocean is tough. Water is heavy and cold. Food can be hard to find. Most octopuses live short lives, just 1 or 2 years. That's barely enough time to learn, let alone pass down knowledge. Even the longest lived, like the giant Pacific octopus, might stretch to 5 years. When octopuses have babies, they lay eggs and then die. The babies hatch alone. No parent to teach them. No time to build up culture. Compare that to elephants or humans, where parents and grandparents help raise the young. That's how traditions and skills spread. And then there's the problem of hands. Octopuses have arms, but they're not like human hands. No bones, no joints, just muscle and suckers. Great for squeezing through holes or grabbing things, but not for building with rocks or sticks. On land, you can pile stones. Underwater, everything is heavy and currents move things around. Try stacking rocks at the bottom of a pool. It's not easy. Fire is another huge problem. You can't light a fire underwater. No fire means no cooking, no metalwork, no way to melt or shape materials. That cuts out a whole set of advances that humans use to build civilization. Even if an octopus wanted to make a tool, it would have to use what it found: shells, stones, or maybe the bones of something else. Writing is also hard. Ink might work for a message, but it disperses fast. Carving into stone or shells is possible, but there's no proof that octopuses or other sea creatures ever tried it. If they did, the evidence might not last. The ocean floor is restless. Sand shifts, mud moves, shells get buried. What about teamwork? Some cephalopods are loners, like most octopuses. Others, like squids, gather in huge groups, but most don't build things together. They hunt mate and move on. No families, no tribes. Without groups, it's hard to share ideas or invent new things. Still, the intelligence is there. That's the part that keeps scientists up at night. Octopuses can solve problems that stump rats or dogs. They play, they explore, and sometimes they even seem to think ahead. There are stories of octopuses escaping from closed tanks, crossing the floor and climbing into another tank to eat crabs, then returning to their own tank as if nothing happened. Now, let's look back in time. Cephalopods have a long history. The group dates back over 500 million years. Early ones had shells. Think of the Nautilus or the extinct Ammonites. For much of that time, they dominated the seas. Some ammonites were as big as truck tires. They floated, swam and hunted in the oceans for hundreds of millions of years. But as far as we know, they didn't build anything lasting. Fossils of ammonites are common. Their shells were hard and coiled. We find them all over the world in rock layers. But inside the shell, the animal was soft. No bones, no hard parts to fossilize. Octopuses, being even softer, almost never leave fossils. Only a handful of fossil octopuses have ever been found. They're rare, delicate, and tell us little about behaviour. So if there ever was a smart tool-using cephalopod, what would it leave behind? Shell piles, arranged stones, unusual marks on the sea floor? Maybe. But after millions of years, the ocean floor gets recycled by plate tectonics. Sediments pile up. Old layers get buried or pushed down into the mantle. Shells dissolve in deep water. Bones break apart. Even if something odd happened, it might be erased by now. But here's a fun twist. In the past 10 years, marine biologists have discovered something called octopus cities. At a few spots off the coast of Australia, dozens of octopuses live close together. They dig out dens, stack shells, and sometimes even interact with each other. Some scientists call these places Octopolis and Octlantis. It's not quite a city. There are no streets or buildings, but it's a step towards social life. The octopuses seem to tolerate each other, maybe even learn from neighbours. Could this be the beginning of something bigger? Maybe if octopuses lived longer and had more chances to pass on their skills, we'd see more complex behaviour. But for now, it's just a strange cluster of dens on the sea floor. Now, let's talk about another ocean group. Whales and dolphins. These are mammals like us, but they went back to the ocean. Some species are incredibly smart. Bottlenose dolphins use sponges to protect their snouts when hunting in sharp coral. Orcas, or killer whales, teach each other hunting tricks. Humpback whales learn songs from each other and change them over time. Dolphins live in pods and have complex social lives. They communicate with whistles, clicks, and even signature calls, like names. They play, solve puzzles, and teach their young. But they don't build. No dolphin has ever made a tool, built a shelter, or left a mark that would last after they're gone. Why not? Part of it is the same as with octopuses. No hands, no fire, and no way to shape the world around them. Dolphins and whales are built for swimming, not building. They use their bodies and brains in amazing ways, but they don't change their environment the way humans do. And there's another problem. The ocean is always moving. Anything you drop gets carried away by currents. Even a pile of shells or stones would scatter. Writing is almost impossible. Songs and calls travel far, but they don't leave a record. Let's imagine, just for a moment, that a whale or dolphin group did come up with a complex language. Maybe they tell stories, share wisdom, or even invent a new kind of hunting. All of that would be invisible to us. Sound doesn't fossilize. Only bones and teeth do. Back to cephalopods. There's one more thing that's worth thinking about. Their bodies are completely different from ours. They're soft, flexible, and can squeeze through tiny spaces. They see the world in a different way. Some can sense light and colour changes that humans can't. Their arms can taste and feel at the same time. If intelligence evolved in a body like that, what would it look like? Maybe they'd use camouflage as language, change colours to signal ideas, warnings, or even stories. Maybe they'd shape the sand into patterns as a way of leaving messages. But all of that would vanish quickly. The next big wave, and the message is gone. Scientists sometimes wonder, are we just being narrow-minded? We look for stone tools, fire pits, or buildings because that's what our civilization leaves behind. What if another kind of intelligence never needed those things? What if their culture was all about movement, colour, or sound? Things that don't fossilize or last in rock. Think about cuttlefish. Again, they have some of the most complex skin in the animal kingdom. With thousands of tiny colour cells, they can create moving patterns, stripes, or even fake eyes. Some use these patterns to hunt, others to hide, and some to communicate. It's like a living light show. Maybe in another world, cuttlefish could have developed a whole language based just on colour flashes, but the ocean erases things fast. Even if a group of octopuses or cuttlefish built a culture, it would vanish without a trace. No ruins, no fossils, no artifacts, just empty shells and shifting sand. Now, let's talk about the deeper ocean. Down where sunlight never reaches, strange creatures live in total darkness. Giant squids, glowing jellyfish, and weird fish with lanterns on their heads. Some of these animals have been around for tens of millions of years. They live slowly, grow old, and rarely meet others of their kind. Could anything intelligent live there? It's possible. We know very little about the deep sea. Every year, scientists discover new species. Some live near hydrothermal vents, hot springs at the bottom, where water gushes out at hundreds of degrees. These vents are like underwater oases. Tube worms, shrimp, and bacteria thrive there, using chemicals instead of sunlight. In theory, a whole ecosystem could develop near these vents, maybe even something smart. But again, no evidence so far. No signs of tools, buildings, or anything built by intelligence. Let's zoom out. If we're looking for a lost civilization in the ocean, what would we find? The answer is almost nothing. Shells dissolve, bones break up, even shipwrecks from a few hundred years ago can disappear. The ocean is a perfect eraser. But maybe we're asking the wrong question. Maybe civilization doesn't always mean pyramids, writing, or metal. Maybe, somewhere in the deep past, there was a kind of culture we can't even imagine. Songs passed down, dances in the water, colour flashes as language, all of it gone, with no trace left behind. Here's something to think about. Humans measure success by what's permanent. Ruins, books, inventions. But nature doesn't care about that. Octopuses and dolphins survive just fine without cities or tools. Their lives are rich in other ways. Exploring, learning, playing, teaching. If a group of octopuses did develop a kind of culture, what would be the signs? Maybe they'd gather in groups, build bigger dens or use more tools. Maybe they'd develop traditions, ways of hunting, ways of hiding, even games. But would any of that fossilize? Almost certainly not. There's one last angle to consider. Time. Cephalopods have been on Earth far longer than humans. They've survived mass extinctions, changing climates and shifting continents. If intelligence is so useful, why hasn't it led to the kind of civilization we see on land? Maybe the ocean is just too hard a place for that. Or maybe intelligence is not always about building things. Maybe it's about solving problems, surviving and adapting. So what does all this mean for the Silurian Hypothesis? The idea that another civilization could have existed before us. The ocean is the best place to hide one, but it's also the worst place to leave evidence. Even if something amazing happened out there, some smart animal building, learning and sharing, It would be almost impossible to find proof today. That's the real challenge. We might be looking for the wrong signs. Or maybe nature just didn't bother with civilization more than once. And this brings us to a bigger question. If civilizations can rise and vanish without a trace, what does that mean for life in the universe? So let's pull back for a minute. We've gone from smart dinosaurs to clever octopuses, from ocean depths to buried cities. But now comes the big idea, the one that keeps popping up whenever we talk about lost civilizations, not just here on Earth, but anywhere in the universe. Scientists call it the Great Filter. It's not a wall or a physical thing. It's more like a giant mystery, and it matters for the Silurian Hypothesis in a big way. Here's how it works. Imagine all life as a long road. At the start, you've got simple things. Bacteria, algae, little blobs that barely do anything. Then, as time goes on, some of those blobs get more complicated. Cells team up. Some learn to breathe oxygen. Others figure out how to eat sunlight. Every step is a hurdle. Some are easy, some are almost impossible. Now, let's say you want to end up with something like us. A civilization that builds, writes, and changes the world. There are a lot of steps between blob and city. Multicellular life, animals with nerves, brains, hands, language, fire, agriculture, tools, cities. Each is a step on the path. At any point, things might get stuck. Maybe life never gets past the blob stage. Maybe it stops at fish. Maybe brains never get big enough. Or maybe even with big brains, nothing ever invents writing or starts using metal. The Great Filter is the name for whatever step is the hardest, the point that almost nobody gets past. If you get through, you're rare, maybe even alone, but most life doesn't make it. Now, why does this matter for our story? Because if there was ever a civilization before ours, dinosaur, octopus, or something else, it had to get through all those steps. And if it did, why don't we see any sign of it now? Did it hit a wall we haven't reached yet? Or did it leave traces we just can't find? Let's break down the possible filters. The first big one is time. Earth is old, 4.5 billion years. But for most of that, nothing happened except bacteria and algae. For over 2 billion years, life was just slime in the ocean. Nothing with a mouth or eyes or even a head. Just tiny things, drifting and dividing. Then something changed. Cells started working together. That led to jellyfish, worms, and sponges. Still nothing smart. It took another 1 billion years to get fish, insects, and plants on land. Dinosaurs finally showed up about 230 million years ago. But for all that time, nothing built a city, wrote a story, or left a message for the future. Here's where people get stuck. If life is so good at getting more complex, why did it take so long for anything smart to appear? Why do we only see civilization in the last blink of Earth's history? Is intelligence rare, or does it just take a really long time? Some scientists think the real filter is getting from simple cells to complex ones. The jump from bacteria to cells with a nucleus, like plants, animals, fungi, was a freak event. Maybe it only happened once. If that's true, most life in the universe is probably still single-celled, even after billions of years. But others think the filter comes later. Maybe brains are easy, but using them for something big, like fire, language, or cities, is rare. Octopuses have brains, but no culture. Dolphins are clever, but don't build. Even among land animals, only a few ever use tools. Most just ate, slept, and ran from danger. Then there's another theory. Maybe civilizations bloom, but they don't last. They rise, change the world, and vanish. Maybe they destroy themselves, or maybe they just die out like any other species. If that's true, the filter is ahead of us, not behind. That's a scary thought, but also an important one. Now let's flip things around. Think about the Fermi paradox, that's the question. If the universe is full of planets, where is everybody? We should see signs of other civilizations, radio signals, ruins, space probes, something. But we don't. The sky is silent. No messages, no Dyson spheres, nothing. The Great Filter could explain it. Maybe it's so hard to get from single cells to cities that it almost never happens. Maybe it's easy to get to cities, but impossible to last for long. Or maybe civilizations always wipe themselves out before they spread to the stars. All of this ties back to the Silurian Hypothesis. If it's so hard to leave a mark, even on your own planet, then maybe the universe is full of civilizations that came and went, leaving almost nothing behind. Maybe we're not alone in being alone. Here's a strange thought. What if every planet with life has its own hidden history? Civilizations that rose and fell but got erased by time, by geology, by their own mistakes. Maybe there were Silurian humans on other worlds, long gone before we ever looked up at the stars. Let's get practical again. What would it take to truly erase a civilization? Not just the buildings, but all evidence. Think about a city. Even if nature wrecks the buildings, some stuff should last, right? Metals, plastics, weird chemicals. But as we saw earlier, Earth is really, really good at cleaning up rain, wind, heat, and shifting ground break everything down. Even plastics and metals turn into dust, or get buried so deep they're never found. But maybe there's another layer to the filter, the self-destruction filter. Civilizations change their world. Sometimes they change it too much. Climate shifts, pollution builds up, resources run out. Wars, plagues, or just bad luck can wipe out everything. If that happens, maybe nothing is left to tell the story. Let's look at real examples. Human history is full of collapsed societies. The Maya, the Romans, Easter Island. Each time something went wrong. Drought, invasion, disease, or just slow decline. In some cases, the cities got swallowed by jungle or desert. In others, people moved away, leaving ruins behind. But even those ruins are recent. Go back further, 10,000 years, 100,000, and almost nothing survives except stones and bones. Now, add in deep time, 1,000,000 years, 10 million. The ground itself moves. Mountains rise. Oceans flood the land. Layers of new rock pile on top. Anything left gets crushed, melted, or buried forever. Even our most durable stuff, nuclear waste, glass, ceramics, wouldn't last forever. Scientists sometimes joke about the archaeologist of the future. Imagine an alien landing on Earth 100 million years from now. What would they actually find? Maybe a few odd mineral layers, tiny bits of plastic in ancient mud, chemical traces in rocks. That's it. No statues, no books, no computers. Our entire story reduced to a thin line in the dirt. Here's where it gets even weirder. Some signals are so faint that you'd never spot them unless you were looking for exactly the right thing. For example, there are certain elements, like plutonium or technetium, that don't occur naturally in large amounts. If you found a big sudden spike of one of those in ancient rocks, it might mean something strange happened. Maybe a nuclear reactor melted down, or maybe someone was making advanced technology. But even then, those elements decay over time. After a few million years, they're gone. So the Great Filter isn't just about building cities, it's about leaving a mark that lasts across time, and that might be the hardest step of all. Let's take a step back and talk about chance. A lot of what happens in evolution comes down to luck. Random events shape who survives and who vanishes. An asteroid hits, a volcano erupts, a new disease spreads. One group gets lucky, another doesn't. Maybe there were 3 or 4 promising starts to civilization on Earth, but all got wiped out by bad luck. Think about the Permian extinction. About 252 million years ago, almost everything died. Up to 96% of ocean species and 70% of land species went extinct. Whatever was here before, it got reset. If there was a smart building species, it's gone. No fossils, no tools, no memory. That's another layer to the great filter. Even if a civilization appears, it has to survive every disaster nature throws at it. Asteroids, supervolcanoes, solar flares, changing climate, you name it. Most don't make it. Now, let's add another wrinkle. Maybe intelligence doesn't always lead to technology. Maybe there are different kinds of smart. Some animals are good at teamwork, others are amazing at solving puzzles, but only humans, as far as we know, turn that brain power into machines, writing and science. Maybe that step, turning thought into technology, is the real filter. Look at elephants. They have big brains, close family ties, and even show signs of grief and memory. But they don't build. Chimpanzees use sticks to fish for termites. Crows make hooks out of twigs. But neither group built cities. Maybe those steps are rare in the universe. Or maybe, as crazy as it sounds, we're the only ones who made it this far. That could mean the filter is behind us. All the hard steps, cells, brains, fire, language, are done. Now we just have to avoid wiping ourselves out. But there's another view. Maybe we're close to the next filter. Maybe the hardest part is surviving your own success. Once you can change your environment, you can also ruin it. Pollution, war, climate change. These are all things that didn't exist until there was a civilization to cause them. If that's the filter, maybe most civilizations collapse not long after they start. This is where the Silurian Hypothesis gets really interesting. If advanced life is rare, or if it always gets erased, then Earth could have had multiple rounds of almost civilizations. Maybe the dinosaurs got close but never quite made it. Maybe there was a group of mammals before us that tried and failed. Each time the slate got wiped clean. New life started over from scratch. And if that's true, then maybe the entire universe is full of planets like ours. Worlds that almost made it, but not quite. Or made it once, but left no sign. Let's talk about how we might spot a lost civilization, even if it's long gone. Scientists suggest a few ideas. Look for weird chemicals in rocks, things that don't belong, plastics, heavy metals, strange isotopes. Or search for odd patterns in ice cores or ocean mud. Evidence of sudden climate changes, unexplained layers. But here's the catch. Nature makes weird stuff all the time. Volcanoes can dump heavy metals into the air. Asteroids can bring in rare elements. Forest fires can leave ash layers. It's easy to mistake natural events for technology, and vice versa. So, if we ever did find a real anomaly in ancient rocks, how would we know it was a civilization, not just a freak event? We'd need a smoking gun, something that can't be explained any other way. Maybe a perfectly regular pattern of chemicals, or an artifact buried deep in rock, something shaped, not natural. But as we've seen, the odds are terrible. The planet is a master at hiding its past. Even if we had the best technology in the world, we might still miss the clues. This brings us to the last big part of the great filter idea, humility. We like to think we'd recognize signs of another civilization, but we only know how to look for things like us. Stone tools, metal, writing, plastic. What if a different kind of intelligence left a mark we've never even thought to look for? What if their technology was something like genetic engineering, or storing information in crystals, or changing the planet in ways we can't see? Maybe the great filter isn't just about survival. Maybe it's about imagination, about being able to recognize what's right in front of us. And this is where it gets philosophical. If civilizations can rise and disappear, leaving almost nothing. What does that mean for us? Are we just the latest in a long line of tries the planet has made? Will anyone know we were here 100 million years from now? Does it even matter? Maybe meaning isn't found in what we leave behind. Maybe it's in the things we do while we're here, the stories we tell, the lives we touch, the mysteries we try to solve. But still, the great filter hangs over everything. It's the reason we keep searching, not just for fossils or ruins, but for answers, for a sense that we're not alone, or that our story fits into something bigger. So next time you hear about the search for lost civilizations, on Earth, on Mars, on distant planets, remember the great filter. It's not just a scientific puzzle, it's a reminder of how lucky and how fragile our moment really is. And now, let's turn the question around. If someone digs up our world far in the future, what will they find? What will we leave behind, if anything at all? When you think about the future, far, far ahead, it might seem obvious that someone someday will dig up traces of us. Our buildings, our junk, our satellites, maybe even our bones. But the truth is, even with all our stuff, the odds are against us, not just because of erosion and time, but because of something deeper. The story of what we leave behind isn't just about what we build, but how the planet changes and what kinds of clues even count as evidence. Let's walk through how a future explorer, maybe alien, maybe human, maybe something else, might go about searching for signs that we were ever here. Imagine it's 100 million years from now. The continents look nothing like today. Most of our cities are long gone. Mountain ranges have risen and fallen. Oceans have swallowed entire countries. Even the stars look different in the sky. So, what could possibly last that long? Start with the easy stuff. Satellites and space junk. Right now, there are thousands of pieces of metal and plastic orbiting Earth. Some are the size of cars, some smaller than a screw. But space isn't empty. There's drag, solar wind, and even tiny bits of dust whizzing by at high speed. Over time, most of those objects will fall back to Earth and burn up. The rest might get knocked out of orbit or break apart. In a few thousand years, almost nothing will be left. Maybe a few larger satellites will keep circling, but even those will eventually come down. Now think about the moon. We've left a lot there. Landers, rovers, even golf balls. The moon doesn't have weather, so things don't erode the way they do on Earth. But there are micrometeorites, tiny rocks hitting the surface all the time. Over millions of years, those impacts will slowly bury or break down anything left by humans. The flag we planted in 1969, it's probably faded to white, maybe even turned to dust. Back on Earth, most of our evidence is even more fragile. Our tallest buildings might last a few thousand years if left alone. But with rain, wind, earthquakes and plant roots, nothing stands forever. Even giant stone monuments, like the pyramids, will eventually wear away. Some might get buried by sand, mud, or new rock layers. Others might fall into the sea as coastlines shift. So for a future archaeologist, the clues get smaller and stranger. Maybe they find a layer of rock filled with microplastics. Maybe they spot a weird spike in heavy metals like lead or mercury where it shouldn't be. Or maybe they notice strange isotopes, chemical fingerprints left by nuclear reactors. But here's the catch. Nature does weird things too. Volcanoes can leave metal-rich ash layers. Meteor strikes can scatter rare elements. Even wildfires can leave odd chemical marks. That's where things get tricky. If you're looking back from the future, how do you tell the difference between a natural event and a sign of civilization? Let's use a real example, the so-called nuclear markers. When we split atoms, like in a nuclear reactor or bomb, we create elements that don't exist in nature, at least not in large amounts. For instance, plutonium-244 and technetium-99. If you found a big sudden spike of one of these in ancient rocks, it could mean something unnatural happened. But even then, those elements don't last forever. Plutonium-244 has a half-life of about 80 million years, so after a few 100 million years it's mostly gone. Technetium-99 sticks around for 200,000 years, but that's still short compared to the age of the planet. Let's zoom in on something even weirder. Synthetic molecules. Some chemicals we make in factories just don't exist in nature. PCBs, polychlorinated biphenyls, for example, are used in electrical equipment and don't break down easily. They stick around in soil and water for decades. But over millions of years, even these tough molecules break apart. Heat, radiation, bacteria, and pressure eventually destroy them. So maybe a future scientist finds a layer of dirt, deep underground, filled with strange molecules or odd ratios of carbon. Could they be sure it was from civilization? Or would they just think it was a weird natural event? Maybe a massive oil fire, a burst of volcanic activity, or a comet impact. Now, let's talk about fossils. Earlier we saw how rare it is for anything to fossilize. Most living things vanish without a trace. Even bones dissolve, get crushed, or are eaten by bacteria. But what about us? Imagine a modern city buried in mud by a giant flood. Some people might get trapped and fossilized, but it's incredibly unlikely. Even if you had a whole city full of people, maybe only a handful would ever turn into fossils. And even then, what are the odds someone digs in the exact spot, at the right time, millions of years later? Here's a funny twist. Animals that live far from civilization might have better odds of being found in the future. Think of a bird that dies in a remote swamp, or a fish in deep ocean mud. Their bones might get covered quickly and stay undisturbed. But humans living in busy cities, the ground gets dug up, paved over or flooded, not ideal for preservation. And it's not just about bones. What about tools? Metal rusts, wood rots, plastics break down. Glass can last a long time, but it shatters and gets ground down into sand. Maybe a few stone buildings or carved rocks survive, but most of what we make will vanish. So what does this mean for the search for ancient civilizations, even ones before us? If we struggle to find evidence of our own existence in the deep future, it's no wonder we haven't found signs of anyone else. Maybe there were earlier tries at civilization by reptiles, mammals, or even sea creatures, but the clues are long gone. Is there any way to spot something that's truly unnatural, even after time has done its worst? One idea is to look for patterns that nature just doesn't make. For example, a perfectly repeating grid of metal in buried rock, or a straight line of holes drilled into bedrock. These are things nature almost never does. But again, everything gets distorted. Over time, earthquakes, magma, and shifting land twist melt and crush even the weirdest shapes. Let's not forget about climate change. Our burning of fossil fuels leaves a clear signal in the rocks and ice. But so do huge volcanic eruptions, asteroid impacts, and even massive forest fires. Sometimes the signals are easy to tell apart. Other times, nature and civilization look almost the same. What about mass extinctions? Some people say if you see a sudden loss of many species in the rock layers, it could mean something big happened. Maybe a disaster caused by technology, like runaway pollution. But extinction events can also come from impacts, volcanoes, or sudden climate shifts. The only way to know for sure is to find direct evidence, something made by hands or minds, not just chemicals. You might be wondering if there's anywhere on Earth where clues could hide, safe from destruction. Some scientists point to stable, ancient parts of the planet, places where the ground hasn't shifted much in a very long time, The interiors of continents shielded from earthquakes or volcanoes might hold buried secrets. Deep caves, salt mines, or thick layers of sediment could trap things for eons. But even then, it's a long shot. Most of what survives is luck. Now let's flip the script. Instead of thinking about cities, what if a civilization never built anything that lasted? Maybe they lived simple lives, used tools made from wood or bone, and left almost nothing behind. Or maybe their technology was so advanced that it didn't rely on big buildings or metal at all. Information stored in DNA, signals sent by light, or machines made from things that break down quickly. In that case, even the best archaeologist wouldn't know where to start. There's one more wild idea. Signals sent into space. Radio waves travel fast, but they fade over time. After a few light years, almost all the signal is lost in background noise. Even if we blasted powerful messages into the stars, it's unlikely anyone would pick them up after a few centuries. Lasers or beacons might last longer, but only if someone's looking in the right place at the right time. So, the evidence for civilization, ours or anyone else's, is thin by nature. Even our best efforts, like sending probes beyond the solar system, aren't guaranteed to last. Voyager 1 and 2 are out there, with golden records meant for anyone who finds them. But space is huge. The odds of someone stumbling across them are close to zero. Now let's get philosophical for a second. If everything fades, if even the greatest works are lost, does that make them meaningless? Maybe not. Maybe the point isn't to leave a permanent mark, but to be part of the story while it lasts. Every species, every civilization gets a moment in the sun. Some moments are shorter, some longer, but all are temporary, back to evidence. If we do find something bizarre in the rocks, a metal spike, a chemical oddity, a fossil with weird features, how do we know it's more than a fluke? Science works by comparing ideas, testing and ruling things out. Right now, every strange signal we've found in ancient rocks has a natural explanation. The carbon spikes, the warming events, the mass die-offs. They all fit things like volcanoes, methane releases, or asteroid impacts. That doesn't mean there's no other story. It just means we haven't found one yet. So, what would be a true smoking gun? Maybe a fossilized circuit board? Maybe a chunk of concrete with a perfect right angle, deep in ancient rock? Or maybe an isotope combination that can't be made by volcanoes or impacts? So far, nothing like that has turned up. But the search isn't over. Scientists keep drilling, digging and testing. Every new layer of rock, every core sample, is a chance to find something unexpected. Maybe one day, someone will spot a pattern that breaks the rules, a signal that can't be explained away. Until then, we keep looking. Let's not forget the limits aren't just about what survives, they're also about our own imagination. Most of our search is based on what we know about ourselves, our chemicals, our tools, our ways of living. But a truly alien civilization, even one from Earth's past, might have done things totally differently. Maybe they left clues we don't even recognize as clues. Here's a question to chew on. If you were planning to leave a message for the far future, what would you do? Carve a mountain? Launch a probe? Build a monument on the moon? Or would you hide the message in DNA or in a chemical code in the rocks? People have tried all these ideas, in one way or another. Time capsules, libraries, messages carved in stone. But all of them face the same problem: nature, time, and luck. Even the most careful plans can fail, and yet we keep trying. That says something about us. Maybe we know, deep down, that being remembered isn't just about evidence. It's about hope, about wanting someone someday to connect with us. Even if it's just a guess, a mystery, a strange signal in the rocks. So, the search for past civilizations is also a mirror. It shows us our own fears, dreams, and limits. We want to know we're not alone. We want to matter. We want to believe that what we do leaves a trace, even if it's just a whisper. And that brings us to the final thought. What does all this mean for how we think about our place here? So, where does all this leave us? After digging through the layers, looking for lost worlds, and thinking about all the ways Earth hides its secrets, the truth is actually a little humbling. The more we learn, the more we realize how small our window is, not just for leaving a mark, but for even being noticed at all. Civilizations, no matter how advanced, are temporary. Even the brightest spark fades. Think about it. We measure time in years, maybe centuries if we're feeling bold. But the planet works on a much bigger clock. Millions, even billions of years tick by. In that sweep, even whole continents come and go. Oceans appear and vanish. Mountains rise, then crumble to dust. Compared to all that, a few thousand years of cities and technology is nothing. A blink. That's not just poetic. It's a fact. If you zoom out far enough, the entire history of humans, every king, every war, every invention, would fit inside a single rock layer. Most of it wouldn't even show up. Bones, buildings, art, even languages, all erased or buried. The odds of someone far in the future finding proof that we were ever here are tiny. And if it's that hard for us, what does that say about anyone before us? Maybe there was a world full of stories we'll never know. Maybe there were creatures who dreamed, built, and wondered, just like us. Maybe they vanished without a trace. Or maybe their traces are so strange, we wouldn't even recognize them as clues. Here's another twist. Even if you try your best to leave a message for the future, you're fighting against the whole planet. You can carve a warning in stone, send a probe into deep space, or bury a time capsule in a mountain. But earthquakes, floods, and shifting land can erase almost anything. Even space isn't safe. Solar radiation, cosmic dust, and collisions can wipe out machines faster than you'd expect. Nothing lasts forever. But maybe that's the point. Maybe the real lesson of the Silurian hypothesis isn't about proof or finding the ultimate fossil. Maybe it's about perspective. We're used to thinking of ourselves as the center of the story, the main event. But the universe doesn't see it that way. Life comes and goes. Civilizations rise and fall. The story keeps moving, with or without us. Let's imagine for a second that someone does find a clue. A scrap of plastic, a weird chemical, a fossil with a tool. What would they think? Would they know what it meant? Or would they scratch their heads, invent wild theories, argue for decades, and maybe never agree? Even now, with all our tools and knowledge, we still debate what counts as evidence. We question our own past. Now picture doing that with clues from a world nobody remembers. There's something comforting in that. Strange as it sounds, we're part of a much bigger pattern. We build, we dream, we try to understand. And even if our traces fade, the effort itself is meaningful. We're not just leaving marks on rocks. We're joining a flow that goes back to the first living thing and will keep going long after we're gone. There's another side to this story. It reminds us to be careful about certainty. Just because we haven't found proof doesn't mean something never happened. Absence of evidence isn't the same as evidence of absence. That's a phrase scientists use when the search is tough. In other words, just because we don't see something doesn't mean it's impossible. Sometimes it just means we haven't looked the right way or in the right place. If we're honest, most of science is guessing with the best information we have. We build theories, test them, look for new clues, and change our minds when the facts shift. The Silurian hypothesis is a perfect example. It's not saying there was definitely a lost civilization. It's just asking, How would we even know? It's a reminder to stay curious and to be humble about what we don't know. Here's what's cool though. The search itself teaches us new things. Even if we never find a lost city or a fossilized machine, we learn about geology, chemistry, biology, and the wild ways the planet works. We get better at spotting patterns, solving mysteries, and seeing our own actions through the eyes of deep time. And maybe, just maybe, thinking about these questions makes us a little more careful with the world we have now. If our time is short and our traces are fragile, maybe it's worth making sure those traces are good ones. Maybe what matters isn't how long we last, but how we spend our moment here. The kindness we show, the knowledge we pass on, the beauty we create, even if it fades. So, what's left after all this talk of lost worlds and deep time? Maybe just a kind of wonder. We're here, right now, asking questions that reach back before memory and forward beyond our own lives. We're part of a story that's always changing, always unfinished. If there was another civilization before us, they're gone now. If there will be another after us, they'll have their own mysteries to solve. That's okay. Our job isn't to be remembered forever. It's to be present, to explore, to dream, and to leave the best story we can. And as you settle in tonight, let yourself feel that. You're not alone. You're part of something bigger and older than any city or machine. You carry the same spark that wondered, built, and hoped in every age. You're a link in a chain that stretches back through darkness and forward into light. Rest easy. Let your mind drift, knowing that you are enough. The story continues, and you're part of it. Good night, and may your dreams be full of wonder.